Okay, hello everyone. Um, so in this video, we will talk about the confidence intervals and hypothesis testing for two means. Okay, for two means, especially for difference of two means, for difference of two populations averages. So we will talk about first hypothesis testing and confidence interval for mu1 minus mu2 when sigma is known. Remember, for the single mu case, we have two different ways of doing this. If sigma is known, remember, if sigma was known, then we just use the z-test, and which says that x bar minus mu divided by sigma divided root n is approximately normal using the sentiment theorem. If sigma is unknown, okay, unknown, then we just use, remember, the t distribution, which says x bar minus mu divided by now s divided by root n. This is t distributed given that the population is normally distributed, okay, or approximately normally distributed. We will just use the same trick here. First, we will deal with the cases when sigma is known, which means we know sigma 1 and sigma 2. So what does this mean? Probably we will use the z-test, okay? And then we will talk about the sigma unknown case where we don't know sigma 1 and we don't know sigma 2, okay? But later we will see that we will just divide this case into two parts. The first part is, well, we don't know them, but we can assume that they are equal to each other. The second part is, well, we don't know them and we cannot assume that they are equal to each other. Okay. So now, let's say this first theorem, which says that, well, if xi's, what does it mean? So if you have n many random variables, xi's, which mean x1, x2, dot, 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 xn, each of them has different mu's and different sigmas, which means each of them has different means, averages, and each of them has different standard deviations or variances, and they are normally distributed, okay? So what does this mean? This tilde sign, and then putting an n here means that, well, this is normally distributed. Okay, so if you have different normally distributed random variables, then their linear combinations, their linear combinations is also normally distributed with some mean mu y. Okay, so let's call this variable y. Let's call this summation as y. So y is normally distributed with its own mean and its own variance, where mean is equal to a1 times mu1, just look at here, a1 times mu1, a1 times mu2, an times mu_n, okay? And its variance is now a1 squared times sigma 1 squared, a2 squared sigma 2 squared, and an squared sigma 2 squared, okay? So for example, let's say if you have um, two normal random variables with x1, which is normally distributed with mu1 and sigma 1 squared. And let's say you have another random variable, normal random variable x2, which is again mu2 and sigma 2 squared. Okay. Then what is the distribution, for example, x1 minus x2, x1 minus x2? That's equal to its expected value is mu1 minus mu2. How about its variance? Its variance is 1 squared times sigma 1 squared plus minus 1 squared times sigma 2 squared, which is equal to sigma 1 squared plus sigma 2 squared. Okay? And we know that, well, this is what? This is normally distributed, okay, with its mean, which is sigma 1 minus mu 2, and its variance, which is sigma 1 squared plus sigma 2 squared. Okay, that's great. Now, using this, okay, using this, so before getting into the slide, now again, let's think how we can use in terms of two, let's say, in terms of two means. Remember, we have for two different populations, for the two different means, we will have x1 bar, okay, and x2 bar. So x1 bar is the sample mean of the first population, and x2 bar is the sample mean of the second population, second sample, sorry. The sample mean of the sample that belongs to the second population, and x1 bar is the sample mean of the sample which belongs to the first population. And we know that they are approximately normally distributed with mu1 and sigma 1 squared divided by n1. Okay, remember from central limit theorem. And this is n. So this is normally distributed again with mu2 and sigma 2 squared divided by n2. Okay, that's great. So what I will try to do is I will try to infer information, okay, infer information, exact information regarding the difference of two means, okay, mu1 minus mu2, mu1 minus mu2, right? So remember, if you want to exact information about mu1, you will just use x1 bar. If you want to exact information about mu2, what does it mean, exacting information? You can use confidence intervals or hypothesis testing. Okay, you will just use the statistic x2 bar. Now I want to infer information about mu1 minus mu2. So what we expect is probably not probably, but we will use x1 bar minus x2 bar, okay? X1 bar minus x2 bar. So x1 bar will say something about mu1, x2 bar will say something about mu2, and x1 bar minus x2 bar will say something about mu1 minus mu2. So remember, in order to say something about mu1 or mu2 here, we need the distribution of x1 bar, or we need the distribution of x2 bar. Now we need the distribution of x1 bar minus x2 bar. But from here, we know that each of them is normally distributed, okay? And from this discussion, we know that, well, this thing here, okay, let me just change my color. This thing here, let me just change into this one into green. So this thing here, in fact, is a linear combination of normal random variables, hence this is normal as well. This is normal, but its mean equal to this one, okay, and its variance which is equal to this. And in fact, we just calculated it here in our sample x1 minus x2. So its mean will be mu1 minus mu2, and its variance will be sigma 1 bar. So the sigma 1 square, so sigma 1 square will be the variance of the first sample mean, okay, and the variance of the second sample mean will be this one. So what is the variance of sigma 1 square? Well, I know this. It's here, okay? Sigma 1 square divided by n1. And for the second one, I know this. It's sigma 2 square divided by n2, okay? So I know this. Let me just come to the second slide. So I know this, right? So x1 bar minus x2 bar, well, that's normally distributed, which mean mu1 minus mu2, okay? And its variance is sigma, what? Its variance is sigma, let's say sigma x1 bar, okay, square, plus sigma x2 bar squared, which is in fact equal to, so this is equal to sigma square divided by n1, okay, plus sigma square divided by n2. In fact, this is sigma 1, okay, this is sigma 2, which means x1 bar minus x2 bar is in fact normally distributed, okay? Sorry for this. Let me just erase this part. Uh, is so normally distributed with mean mu1 minus mu2, and its variance is sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Okay, so this is the approximate distribution of x1 bar minus x2 bar. So let's read our definition. Okay, so if independent samples of size n1 and n2 are drawn at random from two populations, any population, discrete or continuous, which means mu1 and mu2, and variance is sigma 1 squared and sigma 2 squared, respectively, then the sampling distribution of the differences of means. Okay, so the distribution of x1 bar minus x2 bar is approximately normal distributed, sorry, with mean and variance given by this mu1 minus mu2, okay, and its variance is sigma 1 square divided by n1 plus sigma 2 square divided by n2. Hence, okay, so just look at here, this is the normal random variable. Remember what we do with the normal random variables. We just convert them into standard normal random variables, right? How to convert this? Remember, we just write the value of the random variable. So this is the random variable minus its mean, which is mu1 minus mu2, divided by its standard deviation, which is just square root of the variance. And the variance is sigma 1 square divided by n1 and sigma 2 square divided by n2. So this is approximately what? This is approximately a standard normal random variable. Right?